Okay, in Chapter 6, Section 1, we will continue our discussion of the normal curve or the normal distribution. And we've already seen this curve. It's the classic bell shape, so the first question is very simple. We're just looking for this classic bell shape. But we're going to actually now use this to calculate probabilities. So probabilities of things happening. And we can do that because the area under the curve is a probability. So if I have some area here, and this is some x1 value and this is some x2 value, this is the probability that x will be sandwiched between x1 and x2, where x is a random variable. And we can use it for all sorts of things. So people's height, weight, ability in athletics, ability in academics. We can use it to calculate probabilities of people spending certain amounts of money if we're in a business. So it's going to be extremely useful for us. And as I've already argued in this class, the normal curve captures many, many different aspects, be it business or biology as far as how people are constructed, things like that. So we can predict a lot of things with the normal curve. Okay, number 2, the waiting times between, well, let me say one more thing back up here. So the total area under this curve, if we were to look at the entire curve, so if I shaded everything under this curve, that would be an area equal to 1. And so our probability would then also equal 1 or 100%. And then obviously if I don't shade it at all, that would be an area of 0. That would be a probability of 0. Okay, let's look at 2. The waiting times between a subway departure schedule and the arrival of a passenger are uniformly distributed. So I just got done talking about the normal curve, the normal distribution, and now we immediately switch to a different distribution called uniform. So this bus arrives between 0 and 9 minutes. Find the probability that a randomly selected passenger has a waiting time less than 1.75 minutes. Okay, so for a uniform curve, probabilities are still areas under the curve, but the curve is just a rectangle. So we have some A here, some B here. The height of this rectangle has to be 1 divided by B minus A. And if you look at the area of this whole thing, this area equals 1. This is called the uniform distribution. Now let's prove that this area equals 1. Well, the area of a rectangle is just its width times its height. The width here would be B minus A. And the height is given to be 1 over B minus A. So this is the width, this is the height. If you multiply these two things together, you get B minus A on top and B minus A on the bottom, which is just 1. So this is a very, very simple kind of distribution because rectangle areas are extremely easy to calculate. You just have to multiply two numbers together, a width and a height. So now for this problem, it says, find the probability that the person waits less than 1.75 minutes. So this is the probability that x is less than 1.75. And they tell us that the bus will arrive between 0 and 9 minutes. So that would be A, the first number is 0, and B, the second number is 9. So to make this curve, we would have a rectangle. B is 9, A is 0. The height is therefore 1 over B minus A. So 1 over 9 minus 0. And the x value we're interested in is 1.75. So the area we want is anything less than 1.75. So it's this area right here. This area is the same as this probability. So how do we calculate this area? This area would be the width, which is 1.75 minus 0, times the height, which is 1 over 9. So it's just 1/9 of 1.75. And if you do that arithmetic, you will get this area is 0.1944. So what's the probability? Rounded to 3 decimal places, we'll call it 0.194. So there's about a 19% chance that if I'm waiting for this bus, it's going to take less than 1.75 minutes for the bus to get there. Okay, so this whole section, section 1, and then section 2 also, and a good chunk of this chapter is just calculating areas. Now, rectangle areas, I can argue, hopefully you see this and agree, are very simple. It's just a width times a height. But look at this curve. How would you calculate the area of this curve? Well, certainly it's not a rectangle, right? In fact, this is a very complex curve. I teach students how to find the area of a curve like this, not until Calculus 2. So to do this without a table would take some advanced mathematics. So instead of doing that, we are just going to use a table. So we want this area, and we know that we're given a number, z is equal to 0.31. And so we go to a table. And I think I have this in the far back of your notes, of your note packet. It'll look something like this. So actually, let me talk a little bit more before I show you how to do this. So this is called a standard normal curve. Now we calculated z-scores, when was it? Maybe chapter 4, maybe chapter 5. But we have calculated these z-scores, and if you recall, we basically had a standard normal curve. The center is at 0, and then you have 1, 2, 3, minus 1, minus 2, minus 3. So these are z-scores. And if we know our z-score, all we have to do is look up in the table the area to the left of it. So that's one gotcha, is that our tables in this class always give areas to the left of the z-score. Hopefully you'll see that these tables are pretty easy to look up to use. So I'm looking for z equal to 0.31. So it's positive, so I go to the positive z-score table. And over here I have z-scores that are in the ones place and then the tenths place. So we go to 0.3, which would be right here. Then the hundredths place was a 1, and these columns are the hundredths place. So we go to 0.31, the intersection of these two numbers, is our area right here, 62.17%. So 0.6217. And maybe you can kind of eyeball that. So if it was the exact middle of the curve, so if it went right through this hump, this right here would be exactly 50%. And then we're just a sliver past that. So it should be slightly above 50%. Turns out to be 62. Okay, let's look at 4. 4 is the reverse problem. So in 4, they give us the area. They say the area is 0.9756, and they want us to know what, they want us to find out what the z-score is. Well, one thing to keep in mind is right through the center, that's where z equal to 0 is. Anything to the left of that, all of this over here is negative z values, and all of this over here would be positive z values. So we know we are in the positive z value area. So we're going to look in the positive z chart, and now I'm going to look in what I call the sea of numbers for 0.9756. So these numbers start at 50%, half of the curve. They increase as you go down and to the right, and we're looking for 9756. So 9756, here it is right there, 9756. So now we pull the z-score off of this. Let me see if I can show both numbers at the same time. So if I go straight to the left, my starting numbers are 1.9, and then I go straight up 7. So the z-score is 197. 1.97. That gives us the associated z-score that has an area of 97.56%. You're going to see, I'm going to use that table many, many times, so you'll definitely want to locate it in your packet and practice using it. For 5, this is going to be the first example where we have to find an area sandwiched between two z values. So we want the probability that a thermometer reading will be between 1 and 2.25 degrees Celsius. And so the picture for that would be A. So the area is sandwiched between 1 and 2.25. Now this is where it's a little tricky because the table is going to give me areas to the left. So to do this problem, we have to first find z of 2.25, and the area it's going to give me is all of this, but that's too much, right? Because I don't want all of this area here, this white area. I don't want that. So then we're going to find the area at z equal to 1, which is going to be all of this area. And if you can imagine, I'm going to take this area and subtract out this area. So if you can imagine subtracting this chunk out from here, all of this would go away. And can you see that I've got the area I need? So if you can imagine it, subtract out this area from this one, and then I'm left with the sliver of interest. So we have to find two areas here. So minus this will equal the drawing we care about. Oh, I didn't quite do this one right. Like this will give us this area here. Okay, so we go to the chart. I'm going to look for 225. It's positive again. So we would go down to 2.2, which is right here, and then intersect that with the 5 up here, 2.25, and we would get 0.9878. 0.9878 is this area, minus, now we go to a z-score of 1, 1.00 basically, and that would be right here, 1.00, first column, 0.8413. 0.8413. And if you subtract those two numbers, you will get 0.1465. And that is equal to the area of this shaded region. It's also equal to the probability that your z value is sandwiched between 1 and 2.25. So all of those statements are equivalent. And they want you to round to 4 decimal places, so you have to use the table and get it right. No rounding here. That's about as tricky as they get, just having to subtract two numbers at two numbers. Well, let's try just a few more for practice. So 6 is going to be pretty similar to this one. So again, we want to find a probability of the area being sandwiched between two numbers. In this one, the numbers are minus 212 and 361. So the correct drawing would be D. My shading is between minus 212 and 3.61. And just like before, we're going to take the area of the bigger number minus the area of the smaller number. So we're going to take 3.61 and get all of this, and then subtract out minus 212, which would be all of this. Again, it's always areas to the left of these lines, and that should give us the area we care about, the area in between these two. Okay. So let's find an area of 361. So 361 is an interesting one because our table stops at 3.5. So anything bigger than 3.5, we're going to assign 0.9999 to it. So 4 nines. So this is an area of 0.9999. Notice that's almost 1 because we've almost shaded the entire curve. Minus, now this will be the first time we look at the negative z chart. So it's a negative number, so we go to negative z-scores. And we're looking for minus 2.12, which would be down here. Here's minus 2.1 over to 2. So minus 2.12. And that number is 0.0170. 0.017. And if you subtract those two numbers, you should get 0.9829, which is 98.29%. So there's a very, very high probability that your temperature is going to be between negative 212, and 3.61. Oh, this isn't temperature. I guess this is bone density test. So your bone density will be between those two values. Okay, 7. Another one where we have the picture. So it says, assume that a randomly selected subject is given a bone density test. Those test scores are normally distributed with a mean of 0 and a standard deviation of 1. Draw a graph and find the probability of a bone density score less than 0. So less than 0 is saying, what's the probability that z is less than 0? Well, 0 on the normal curve is exactly in the center. So the only two possible options would be B and D, because those are the only two that put 0 right in the center. Now, less than that is to the left. So this is saying left of 0. So the correct shading would be D. We want the shading to the left of 0. Now, you don't even need to look this up in the chart, although we can. This is cutting exactly half of the curve. And I said the whole curve is 1, so half of the curve would be 0.5. And we can check that. Just go to a z-score of 0. Z-score of 0.000 is 0.5000. So it's exactly half of the curve. Are these areas and tables making sense? Okay. Hopefully you're not confused by the tables, because we're going to end up using them a lot going forward. Okay, 8. This is the hardest problem in this section for sure, so let's take our time and stop me if I lose you. For bone density scores that are normally distributed with a mean of 0, standard deviation of 1, find the percentage of scores that are A, significantly high, or at least 2 standard deviations above the mean, significantly low, or at least 2 standard deviations below the mean. So 2 standard deviations just means it's a z-score equal to 2. So what we have is, here's a z of 2, and they want the percentage above the mean, above this number. So they actually want this shading. Now here's the problem. Our table is going to give us this number. But in this problem, they don't want this number. They want above it. So let's first find this number, and then we can talk about what we'll do. So we look for a z of 2. So it's positive. So we'd go down here to 2.000. So 2.0, and then 2 more zeros. So it's the first, this row, 2 row, and the 0 column. And so the area there would be 0.9772. 0.977. So this white area is 0.9772. Now keep in mind, this whole curve has to add up to 1. So to get this area, I will take 1 minus this. Did everyone see that? So to get this unknown area, we will take 1 minus this area we looked up. And if you do that, you should get this area is equal to, it's just 1 minus 0.9772. If you do that subtraction, you'll get the area is 0.9772. 0.0228. And they want that as a percentage, so we'll jump this decimal 2 to the right and call it 2.28%. So there's a 2.28% chance that a person's bone density score will be 2 standard deviations above the mean or significantly high. Okay, let's look at the significantly low one. This one would be 2 standard deviations below the mean, so it's over here on the left side. And it becomes a -2 because it's to the left of the center. And they want this area. So the nice thing about this one is there is no subtraction I have to do. I can just look this area up. So we go to a z-score of -2 now. So we'll go down to -2.0, and then it's -2.000, so the first column, and the number is 0.0228. 0.0228. And so to convert this to a percentage, jump the decimal 2 to the right, and it's 2.28%. And what do we notice about these two answers and these two answers? They're the same. And that is the nice thing about the normal curve, is that it is symmetric. So scores like -1 and 1, -2 and 2, -3 and 3, they will have the same areas. So we actually could have saved ourselves some work knowing that. We could have looked up this one and then said, oh, by symmetry, this one will be the same. And it doesn't even have to be whole numbers. If you had -1.5 and +1.5, that would work too. So any number, as long as you have the plus and minus, will have the same areas. Okay, so this would be a significantly low bone density score. So now it says, what's the percentage of bone density scores that are not significant? So that is asking for the area in between those two values. So they want to know, in this last question, what is this area? Well, if we know this one is 0.0228, and this one is 0.0228, and the whole thing has to add up to 1, then this area would just be 1 minus this 0.0228 minus this 0.0228, and that should give us the area here, the area in between. And if you do this subtraction from 1, you will get 0.9544. Percentage would be 95.44. And I'd be impressed if you remembered it, but you might. A long time ago, I drew the standard normal curve, and I drew these two flags, and I said 95% of people will be between those two flags. And now we just proved it using the table. It's a bit of rounding, but for a quick rule of thumb, you can say 95% of people will be between plus or minus 2 standard deviations from the mean. Any questions on that one? Because that one's probably the trickier of these problems in this set today. Okay, then our last two are just kind of a vocabulary refresher. So let's look at it. 9 says, which of the following groups of terms can be used interchangeably when working with normal distributions? areas, z-scores, and relative frequencies. So a z-score is a number. It is not an area. So a relative frequency is an area. So this one and this one are the same, but z-scores doesn't fit that pattern. Z-scores, probability, and relative frequencies are also areas, but z-scores are not. Areas, z-scores, and probability, we just said z-scores aren't areas. Areas, probability, and relative frequencies. Yes, these are all the same when you have a normal curve. Z-scores are lines, and a line can't have an area. Which of the following does not describe the standard normal distribution? The graph is uniform. So the uniform curve looks like this, but the standard normal curve looks like this. So these are definitely not the same thing. So this is the one we throw out right away. The total area under the curve must equal 1. Yes, that's true. We saw that. The graph is symmetric. Yes. So between this line, z equals 0, this is symmetric about that line. Yep. It is a normal distribution with a mean of 0 and a standard deviation of 1. Check. Okay, so that'll complete section 6.1.